Okay, so before I continue, any questions? No, so let me move on to the next one. So actually we have three types of losses. The first one has loss, but right now let's check slow fading and fast fading. For slow fading we call it long-term fading. So that you never know, okay, after long term then we will have a change, so it's long term fading. And fast fading actually is a short term fading. And so that we have further fluctuations. Of course, right now we have the way of changing, so we can see all the possible changes. If we check the scale, sometimes the scale is more this one. And the scale will be larger, and the scale for really large. And so we have the three types of losses, from fast loss to slow fading to fast fading. Well, fade, what it means here. If we talk about trends, actually these trends will decrease gradually, and this is called fade. And we have the fast, so we call fading. Because we discussed past loss in the past section, but right now let's continue to check the second one, slow fading. So slow fading here. So you can check what it means, slow fading. Caused by movement over distance. And the distance actually large enough to produce growth variation. And so that this one, it is called slow fading. And also called the long-term variation. And so that we have the corresponding distribution later. And this one, if long-term, and we also call it shadowing along normal fading. Right. And when we talk about the second shadowing of the corresponding one, we will have the log normal to be included to describe the signal changes. And so that here we have the log normal distribution. And log normal distribution used to describe the signal label. Alright, so log normal. What is the form for log normal? Firstly, we talk about the probability theory. So we know log normal, right? And here, let me ask you the question. The current form you have, it's normal or log normal? the current from here is normal or not normal? If you think it's normal, raise your hands. Not normal? The answer is normal. But why not normal? If we have the original quantity, taking logarithm first to have the value in terms of logarithm, then using logarithm to check the distribution. If logarithm follows normal, then this kind of distribution we call log normal. So log normal, sometimes we have the operation inside the name. Taking logarithm, then follows normal distribution. If so, this kind of signal distribution should follow the so-called log normal. So understand the meaning? I don't know log normal. And the thing about this, why this one we have log? Because the current distribution in terms of decimals. Right? Decimals actually taking logarithm first. And of course, because of logarithm, so log already here. And normal, so we have a normal. And where to have the log normal distribution? If we care about the original signal label, not in terms of decimals, and then that signal strength follows the log normal distribution. Alright, so in fact, for the current signal we have, it follows log normal. However, for the current signal strength, if we take logarithm and then what's the distribution for the logarithm value of signal strength, it's normal. Alright, so normal or not normal here. Can you tell which one is normal or which one is not normal? Alright, so even I don't know the answer, but let me repeat the question again. If we consider signal strength without any decimals, this is first type of a signal. And the second type of a signal is the signal strength taking logarithm. And so that we pass out the logarithm value, and then we have the corresponding distribution. So let me ask you, first of all, for first case, which distribution we have if we consider a shadowing of slow fading here? It's log normal or normal? It's log normal. But for the second one, taking logarithm already, so what's the distribution? It's normal. Alright, so this is the way to have the log normal distribution. Well, so of course normal can be shown easily, so we use normal, and we want to use it to describe the signal strength. Of course, we need to show all the signal label in terms of decimals, and so that we can have the log normal distribution. So shadowing actually says, if you can have theory, actually we can have the formula to govern the signal strength. What kind of distribution to govern the signal strength? Actually, log normal to govern the signal strength. Alright, what I mean shadow here. And current is same. Current shape, the bell shape is normal or log normal? The current bell shape is normal or log normal? Normal, correct. Okay, so allow you to serve as a presenter. Sure, go ahead. Allow the TA know. Yeah, it's normal. Because of normal, then we will have the bell shape. But why this one normal? Because we have a signal label but in dB. Alright. However, if we don't want to have a dB using the original value to have the proper distribution, then what's the distribution? Anyone want to try? Yeah, log normal. So understand currently log normal and the normal relationship. Alright, Sam, you can indicate you are the presenter. Well, so that's the shadowing, that's the slow value. And the fast value actually we still can employ the other distribution to describe fast value. And so we will have the later formula, but even complicated, but we check how to have a fast value. Here it says, reflected from objects, hills, building, vehicles, and this one is a normal one. Fast value due to scattering of a signal by object near transmitter. Alright, and how to have the signal strength expression? Actually, we can have these. Receive signal, we can describe this by Rayleigh distribution. As for Rayleigh, actually from the probability theory, you can look up what it means Rayleigh. And Rayleigh here, actually we will have beta equal to 0, so that is Rayleigh. But the current formula, actually it should be Rayleigh formula. Alright, so Rayleigh, and then we can use them to describe the signal strength of the fast value. And we have some parameter distribution, you can try to check these. Specifically, we relate some results to the Bessel function. Alright, so this is the result. So the other middle value, you can try to check middle. Alright. And here, actually, beta equal to 0, then we have a Rayleigh distribution. And Rayleigh distribution, if we further check parameter sigma, then we have the different outlier variation. Okay, like this one. So it doesn't mean we have beta equal to 0. If not 0, then we have this one. Oh, okay, then this kind of term then we call Rayleigh. And Rayleigh still related to 0 order Bessel function, like this one. Alright, so this is the Rayleigh. So Rayleigh and Rayleigh, and normally actually we have the different application. Rayleigh actually talking about the mean, the label is non-zero. But for Rayleigh actually the mean is it's 0. So this is the difference. And so then Rayleigh we have the sharp envelope for the distribution. And crazy, we gotta know, oh okay, where we have the Rayleigh actually when the parameter beta equal to 0, then that one is Rayleigh. As for the others, actually they are Rayleigh. So the parameter here, except for beta equal to 0, the others actually follow the parameter of a Rayleigh distribution. So all these serving as the distribution to allow us to have the distribution for the fast varying signal strengths. Alright, that's it. So let me stop here, and because we have some definition. So maybe it doesn't mean I want to hurry up to go through all the slides in chapter 3. So let me stop and let you think about this one. Fading from it should be from even from passive to slow fading, finally to fast fading. So think about what kind of content you have, and also why finally we have the function Rayleigh and the other function to describe fast fading. Okay, now you have 3 minutes to discuss with your neighbors. Okay, go and check it. If you want to have slides, we can have the slides on Moodle. You can download the slides from Moodle. Of course, I will update for you possible champions. So even we still have 40 seconds, but let us check the next one. Oh, okay, if we care about signal labeling, so we have the characteristics of instantaneous amplitude. Instantaneous amplitude, then we care about the following terms. So we have some definition. We have a signal label. We can set a label there. Can we have the possible times of label crossing? And so that we have a label crossing rate. If a label crossing rate, what it means? Every number of times per second that the signal after cross the label specified in positive going direction. For example, positive O, cross it, but finally get back to negative and positive. So we care about one direction, positive going direction. And that rate is called the level crossing rate. This is the first one. So it doesn't mean, oh, okay, upward and then downward. No, just upward only. No downward here. And the second one, fading rate. Previously, we have the definition of a label middle. I don't mention middle, but you can follow the previous way to have the middle value. And we set the middle value as a label of to be crossed. And so that if we count the number of signal after crosses middle value in positive direction, and it's called the fading rate. Therefore, fading rate is a special case of the general level crossing rate. What kind of a level crossing rate? It should be the reference label be the middle level, and middle level to be crossed, and then it's the fading rate. And the depth of fading, then its ratio. There's someone like, oh, okay, we have the value effect. No, here, depth of fading is ratio. And ratio of mean square value and the minimum value of fading signal. So we select one fading signal, and if we can find mean value and the minimum value, the ratio is called the depth of fading. Finally, the fading duration. Oh, the time interval for which signal, and it is below the specified threshold, then this is called the fading duration. Alright, allow you to have 2 minutes to think about the definition here. Level crossing rate, fading rate, depth of fading, and the fading duration. Likewise, we still have 30 seconds, but let me move on to the next page. This is called the frequency shift, and this kind of shift because of mobility and also the frequency. So we have the Doppler shift. And Doppler effect, actually you can check this. When a web source and receiver they are moving towards each other or something else, then the frequency of the received signal will be changed properly. The formula here, carrier frequency minus this one, and we have B over lambda multiply the angle, it's theta. And this way we call the Doppler shift, so that you will have the frequency shift follow the principle, Doppler shift. Well, later we will use it, so you can check this one properly. So the direction of there, the direction of a moving signal, and this is the speed, and so that we will have an angle. And for the formula here, actually, we try to have the way to, in fact, to increase or to decrease. We will follow the formula to have the calculation. And next one, moving spray effect. Spray actually, we will spray to the out, so spray out. And why? Because we don't have the single pass, we have the other propagation effect. So we have the shift to the other side, so we have the separation. So this kind of effect we call moving speed effect. And previously we have a delay spray. So delay spray actually we have a different time to reach the destinations. Of course, this kind of effect we call the delay spray. And this kind of delay spray. And delay spray actually can be sprayed to the other area, and this is called the frequency of delay spray. And here you then know, oh, okay, we have the different situation because of the reflection, etc. So we have the possible waveform coming from different reflectors. So for example, the signal from the close by refractors, and this one intermediate reflector, and the others far away reflectors. this is inter-symbol interference. Well, inter-symbol interference, actually we have a symbol. The symbols won't affect the other, so that's the perfect design. But however, for the real situation, no. We will have the different waveform put them together, so we have the received signal to become larger or become smaller. It really depends on the possible interference. So, ISI actually inter-symbol, and the interference from the symbol will interfere that symbol, and this kind of interference we call inter-symbol interference. And actually to avoid inter-symbol interference, we should follow the relationship. So the rate is actually governed by the value, and the value actually is tau d. So this is a researcher's development to know the relationship, and you can follow the relationship to specify the possible tau d delays rate. Alright, so again, let me stop here for you to have a discussion for some definition and some phenomena. Okay, go and check it with your classmates. Your teammates. Alright, so maybe still have a few seconds. This one defines coherence balance. So coherent balance actually, this is a different separation, this one. To find signal angle at a different signal, and then the difference is called the coherence balance. So for the others, I think you can check it. So what it means is coherence, this one. You can check the real meaning if you don't think this one fits the current discussion. Well, cochannel actually in chapter 5 or there no cochannel. Cochannel says, oh, within the cell I use channel 1. And the other cell also use the same, so we have the cochannel interference. So of course, cochannel interference we should have the same frequency, interfere with each other, and later we will have some parameters. So this one. If we specify some facial and desired one, and if still low, then this is a cochannel mobility. Why a term cochannel mobility? I don't have any idea, but impossible. You don't care about the name, you just care about the corresponding probability. And then we can find for example, for the company, Of course, we don't. Actually, we don't have the. Actually, we expect we have the same one, so we don't have this case and try to avoid it. But actually, we still incur this kind of interference of we have for the setting. So this is the desired one. Alright, and desired one maybe specify the ratio still loading. Maybe you think this one still have the interference or some other things. But we can define this and later we can have the corresponding formula. So, if we go through chapter 3 just talk about the terminologies and think about this. Going through all the terminology, which one you think you know them well. So, if yes, then you can put the term to the words cloud, and the words cloud will check your understanding about the terms of the chapter. And so that I know you know that exactly, or you still need to refine to have the exact terms. Okay, then you have 2 minutes to think about the term and also key in the term. And finally, you can have these. But before I go, let me measure. Can you have the pole here? Can you see? Okay, good. Yeah, Haslow is correct. And fatty duration. And we have the propagation to cause all the possible issues. And we have an antenna, and antenna can have the different gain. That's correct. And we have fatty can employ the distribution log normal. And log normal actually is the original term shadowing effect. Oh, okay. That's all almost known by you. So that means natural, not finished recipients. Alright, so finished for all of you, then we move on to the next one. So this is the content we explain. And later I try to assign a problem. Even later we don't have enough time, but summarize serving as a preparation. Take the picture first. And then we have 10 minutes to have the discussion with your. Let me have A first. And let me assign. We have a 4. So, okay. Actually, we have 5 sub-problems. First one, let me assign to Group 2. Group 2. First problem. And the third one, 3.9 by Group 1. And solid sub-problem of the second problem A and B by Group 3. C by Group 4. And also we will have the answer for all of the questions. So I will ask you to share share your reference solution, and besides, you should understand how to have the answer for the other question as well. But I assign some of the team to have the reference solution. If you think, okay, you want to know all of this, sure, you can know. But initially, try to figure out how to have the solution. Likewise, you can use ChatGPT to find the possible answer. Go and check it. 8 minutes. So if possible, you can try to rotate your table to have the other discussion. If you don't think so, sure. Currently, at least you get closer, so you can have the way to have the proper discussion for sure, no problem. So actually for this one, where we can help to form your problem, some problem C, right?
Yeah.
So which one do you think you can apply to? Yeah, true. That's true. And how do you check it?
Yeah,
true. Of course, you can share the information with your teammates.
maybe you remember my answer
So I think you know where to have the phone. As a challenge, you should find the proper definition. Go and check.
飞点做什么？社区来，有电影我会社区来，然后去。